In this lecture, I would like to discuss about the general properties of interhalogen compounds. In previous lecture, we has been discuss what are the interhalogen compounds. Interhalogen compounds are those compounds in which the halogen elements combine themselves. Number of interhalogen compounds are formed. For example, iodine monofluoride, iodine monochloride, bromine fluoride. So these compounds are called as lower interhalogen compounds. Iodine fluoride, iodine fluoride, iodine bromide, then iodine trifluoride, iodine pentafluoride, iodine heptafluoride. So these compounds are called as higher interhalogen compounds. So we know that in interhalogen compounds, one of the halogen element shows positive oxidation state and another halogen element shows negative oxidation state. So let us discuss now the general properties of interhalogen compounds. The first property, it is the bond strength of the interhalogens or bond energy of the interhalogen compounds. Bond strength or bond energy of interhalogen compounds. So the bond strength of interhalogen increases as the electronegativity difference between the halogens increases. Larger the electronegativity difference, greater is the bond strength. Larger the electronegativity difference, greater is the bond strength. For example, if we take three examples here, iodine monofluoride, iodine monochloride, and iodine monobromide. So in these three interhalogen compounds, the electronegativity difference between the iodine and fluorine is larger. Fluorine is the most electronegative element and iodine is the less electronegative element. So as the electronegativity difference will be larger, the extent of ionic character between the iodine and fluorine will be larger. So iodine carry positive charge and fluorine carry negative charge. So the bond strength will depends upon the difference between the electronegativity between the two halogen elements. It is also known that a bond with partial ionic character is a stronger than a bond which is purely covalent or purely ionic. Now, in case of iodine monofluoride, there is a partial ionic character as well as covalent character. So, whenever there is a partial ionic character and covalent character, the bond becomes very stronger. So, the bond strength of IF is stronger than ICl and IBr. Okay, so it means that uh, the bond energy of IF is also stronger. Okay, now second property, the heat of formation or enthalpies of formation, delta H F0. So the heat of formation, it is the heat energy released during the formation of 1 mole of the interhalogen compounds. So as the heat of formation of the interhalogen compounds decreases, then the bond strength is also decreases. So the heat of formation of interhalogen compounds decrease with decrease in electronegativity difference. Decrease with decrease in electronegativity difference. For example, you can see here IF, the electronegativity difference is larger as compared to ICl as compared to IBr. So as the electronegativity difference is larger, the heat of formation is also larger, and it will further going to be decreases. It means that IF is having larger heat of formation or enthalpy of formation. It means that during the formation of the IF, the larger energy is released, greater heat energy is released. Therefore, IF is more stable compound, and also we know that the bond strength of the IF is greater. Let us see now the another examples, the IF, BRF and CLF. In case of the IF, the electronegativity difference is larger between iodine and fluorine. You can see here, the iodine is having the electronegativity in this table. The electronegativity of iodine, fluorine, bromine and chlorine is mentioned. The electronegativity of iodine, it is 2.52 and 3.90. So in case of the ion, IF, this electronegativity difference is 1.38. So let us here, the electronegativity difference, it is 1.38. In case of BRF, the electronegativity difference between the bromine and fluorine, it is, if we take this difference, 3.90 minus 2.62, it is 1.28. So this is less. In case of CLF, the electronegativity difference, once again it is less, it is around 0.95. So as the electronegativity difference is larger here in case of the IF, the heat of formation is also greater. So you can see in this table, the bond energy is also given. For IF, the bond energy, it is 277.8. It means that IF is more stable. Okay. And BRF, the bond energy is less. CLF, the bond energy is less. So it means that the bond strength, it is also less here in case of the CLF, in case of the BRF. So bond strength will be greater. As the bond energy will be higher, the bond strength will be greater. It means that the IF is a more stable compound as compared to CLF. So this is about the heat of formation and the bond strength among the interhalogen compounds. So generally it will depends upon the difference between the electronegativity between the two halogen elements. Now third property, which is very important, it explains the oxidation state of the interhalogen compounds. We know that in interhalogen compounds, the lower halogen element, the less electronegative halogen element shows positive oxidation state, and more electronegative halogen element shows negative oxidation state. For example, in IF, as iodine is less electronegative, so uh, it is having positive oxidation state, and fluorine, it is more electronegative element, so ultimately the electron goes to the fluorine, electrons are shifted to the fluorine, so it is more electronegative element, so it means that fluorine is the electrons are migrated to the fluorine. Okay, so in interhalogen compounds, the less electronegative halogen exhibit positive oxidation state. The less electronegative halogen exhibit positive oxidation state, and more electronegative halogen element shows negative oxidation state. So in IF, the oxidation state of iodine, it is +1 and fluorine, it is -1. The interhalogen compounds have the less electronegative halogen as the central atom. In the formation of the interhalogen compounds, we know that the central halogen atom, it is the less electronegative halogen element. Okay, the central halogen atom exhibits higher positive oxidation state. As we know, the general formula of the interhalogen compound, it is XYN. So in this general formula, X is less electronegative element and Y is more electronegative element. And the value of the N, it is equal to odd number 1, 3, 5, 7, like that. So this less electronegative halogen element shows +1, +3, +5 and +7 oxidation state. Okay, the less electronegative halogen shows the oxidation state from +1, +3, +5 and +7 oxidation. So how it is possible such higher oxidation state? Particularly the iodine is the element which is showing such type of the higher positive oxidation state. So let us see iodine. So iodine, it is having the atomic number 53. So it is having the electronic configuration krypton 4d10 5s2 5p5 and 5d0. So there are 7 valence electrons in the valence shell of the iodine. As we know, iodine is less electronegative. Also, the atomic size of the iodine is larger. So in the ground state, iodine shows the electronic configuration 5s2 5p5. So there is only one electron is there. In excited state, uh, the promotion of the electron is takes place from this 5p orbital. This electron, it is shifted to this 5d orbital. Okay, so there are three half filled orbitals now. So iodine in excited state undergoes sp3 dehybridization. This is s orbital, 5s orbital, 1, 3p orbitals. Okay, 3p orbitals here. These are the 3p orbitals, 5p, and this is 5d orbital. So 1s, 3p, and 1d. So hybridization, it is sp3 dehybridization. And what is the oxidation state here? Plus 3 oxidation state. As there are 3 unpaired electrons in the half-filled orbital of the iodine, it shows plus 3 oxidation state. Now we can show the next here. The promotion of the electron from this one of the 5 orbital to the next 5d orbital here. Okay. So now the hybridization will be changes. The half-filled orbitals are 1, 2, 3, 4, 5. Okay. So iodine shows here sp3 dt sp3d2 hybridization. This is s, this is p, and 2d orbitals are involved into the hybridization. And in this case, oxidation state of the iodine, it is plus 5 here. Here it is plus 3, and here it is plus 1. As there is only one half-filled orbital, only one unpaired electron, so it shows plus 1 oxidation state. And last one, uh, the highest oxidation state of the iodine is possible because this electron from the s orbital, it is goes to the d orbital here. So now there are 7 half-filled orbitals. You can see 1, 2, 3, 4, 5, 6, 7. 7 half-filled orbitals are there. So hybridization will be sp3d3 hybridization. So iodine undergoes the hybridization in plus 1 oxidation state. Iodine undergoes the hybridization. It is sp3d. This is sp3d hybridization. Okay, 1s 3p. Sorry, sp3 hybridization. It is sp3 hybridization in plus 1 oxidation state. In plus 3 oxidation state, iodine undergoes in plus 3 oxidation state. It is sp3d hybridization. In plus 5 oxidation state, it is sp3d2 hybridization. And in plus 7 oxidation state, it is sp3d3 hybridization. So iodine shows such type of the higher oxidation state. There is some specific reason. Chlorine and bromine does not show this behavior because the atomic size of the chlorine and bromine is shorter. So the promotion of the electron is not possible, and also the ionization energy are higher as compared to the iodine. So in the ground state, iodine has single unpaired electron, as we have seen. It forms a single bond with another element in its compound. If the other element is more electronegative, that is fluorine, like this, so there is a formation of the IF where iodine shows plus 1 oxidation state and fluorine shows minus 1 oxidation state. So in iodine fluoride, okay, so iodine shows plus 1 oxidation state and fluorine shows minus 1 oxidation state because fluorine is more electronegative. And when iodine undergoes sp3d hybridization in a compound, it has 3 unpaired electrons. It has 3 unpaired electrons. Okay, and it forms 3 covalent bonds in IF3, and the compound it is IF3, where iodine undergoes sp3d hybridization, in which the oxidation state of the iodine it is plus 3. Similarly, when iodine undergoes sp3d2 hybridization, there will be 5 unpaired electrons, and iodine forms 5 covalent bonds, and the compound it is IF5. And in IF7, iodine undergoes plus 7 oxidation state, and hybridization is sp3d2 hybridization. So thus iodine shows higher oxidation state. Only iodine exhibits higher positive oxidation state, plus 1, plus 3, plus 5, and plus 7. That oxidation state, it is not possible in case of the other halogen elements. The tendency to form interhalogen compounds at higher oxidation states depends on. So why only the iodine shows higher oxidation state? Why not chlorine? Why not bromine? The reason is that the electronegativity. Iodine is less electronegative. Second thing, atomic size. The atomic size of the iodine is larger. Lower the electronegativity and larger the atomic size, greater is the tendency to show the positive oxidation state. That's why iodine shows positive oxidation state from +1 to +7. Among the halogen, iodine is the only one element which undergoes such type of the oxidation state, and it forms iodine heptafluoride. It forms iodine heptafluoride. Other halogen does not shows. Iodine only undergoes the positive oxidation state, that is +7, and it forms iodine heptafluoride IF7. While there is no ClF7, no BRF7. Okay, bromine and chlorine does not undergoes because the atomic electronegativity difference between the chlorine and bromine, fluorine, it is less. Same will be here. Now, fourth general properties. Interhalogens are more reactive than halogens, except fluorine. Okay, interhalogens are more reactive, except fluorine is very reactive. Interhalogens are also reactive, but other halogen, Cl2, Br2, and I2, interhalogens are more reactive than them. Okay, this is on the basis of bond energies of chlorine, bromine, and iodine molecules are more than interhalogens. Therefore, interhalogens are better halogenating agents as compared to the halogen elements, halogen molecules. Interhalogens reacts with metals forming mixed halides. You can see here. Magnesium metal. This is iodine chloride, monochloride. Okay. So there is a formation of mixed halide, magnesium iodide and magnesium chloride. It means that this interhalogen compound is very reactive. Okay. So the order of reactivity of some interhalogen compounds, it is given here. Order of reactivity. So chlorine trifluoride react to bromine trifluoride IF7, BRF7, IF5, BRF. So this is about the reactivity of the interhalogen compounds. Then fifth property, solubility of interhalogen compounds. Interhalogens are soluble in organic as well as some inorganic solvents. Okay. Interhalogens conduct the electricity in their solution as well as in their molten state due to partial autoionization. Due to their partial autoionization, they can be ionized. Okay, so they are the solution of the interhalogen compounds conduct the electricity. Next property, the thermal stability of interhalogen compounds. The thermal stability of XY type of interhalogen decreases with decrease in electronegativity difference between the X and Y. As the electronegativity difference decreases, the thermal stability is also decreases. Previously, we know bond strength will be decreases when the electronegativity difference will be decreases. For example, in iodine monofluoride, the electronegativity difference it is 1.5. In bromine fluoride, the electronegativity difference it is 1.2. In chlorine fluoride, the electronegativity difference it is 1.0. In iodine monochloride, it is 0.5. In iodine monobromide, it is 0.3. In bromine chloride, it is 0.2. So it means that this is the thermal stability of XY type of the interhalogen compounds. So IF is highly stable. As the electronegativity difference will be larger here between the iodine and fluorine, it is highly stable. It is thermally stable. Okay. So from the above observation, it is clear that more polar the bond XY, greater is the stability of the interhalogen compounds. So this bond is more polar because iodine is less electronegative, fluorine is more electronegative. So it is having the higher thermal stability as well as higher bond energy as well as it is having higher bond strength. So the thermal stability of the interhalogen compounds decreases with decrease in electronegativity difference. So this is about the thermal stability. Now seventh property, interhalogens undergoes addition reactions. As interhalogens are reactive, they can show some organic reactions. Okay, generally XY type of the interhalogen compounds add into the ethylenic double bond. they will be add into ethylenic double bond. So you can see here the reaction here. The reaction is shown here. So ICl is the best example of this type. It is used as a Weiss reagent. ICl, it is used as a Weiss reagent. This is the organic reaction. So it is added into the ethyl molecule. It is added into the ethylenic molecule. Okay, you can see here. So let us see. Addition of iodine and chlorine. Double bond get breaks and iodine and chlorine gets added here. So this is the addition reaction. Interhalogens undergoes addition reaction. Now let us discuss the very important general property of the interhalogen compound. It is disproportionation. Interhalogens undergoes disproportionation. So what is disproportionation? Disproportionation means it is interhalogens undergo oxidation as well as reduction simultaneously. Means they are showing the redox reaction. And lower interhalogen compounds are converted into the higher interhalogen compounds. Therefore, it is disproportionation. From lower interhalogen compounds to higher interhalogen compounds, the conversion is there. So you can see now this reaction. So iodine monofluoride is converted to iodine pentafluoride. Okay. So now 5 molecules we have taken here. Okay. 5 molecules are there. And why this disproportion is takes place? The reason is that there is a gain in the bond energy. Whenever the conversion is takes place, if there is a gain in the bond energy, then the interhalogens undergoes disproportionation reaction, otherwise not possible. So you can see here 5 IF bonds are there. So the bond energy of iodine fluoride it is 277.8. So 5 multiplied by this. Now I would like to calculate here the gain in bond energy or loss in bond energy. Now the bond energy of the I2 molecule, this bond energy of this I2 molecule, it is 149 kilojoule per mole. Two I2 molecules are formed here due to the conversion of these 5 IF molecules. And this higher interhalogen compound, it is formed IF5. So 5 bonds are there here also. 5 bonds are here, okay? IF bonds like this. This is in this way, okay? So now in this case, in IF5, there are 5 IF bonds. So the bond energy it is 267.8. There is a difference, even the bond is same, but bond energy will be highest here. Now this in IF5, the single bond covalent bond energy it is less because crowding is there, bond energy get decreases. As the number of bonds increases, the fluorine atoms associated with the central iodine atom, so it destabilizes the molecule. So bond energy will be less here. Okay, in case of the IF5 as compared to the IF. So if we calculate this, this is 1389 and this is 1637. So the energy of this minus the energy of this, so the difference in energy it is 248 kilojoule per mole. That's why IF is converted to IF5. Conversion of lower interhalogen compound to higher interhalogen compounds. And it also undergo oxidation as well as reduction. How oxidation is there? What is the oxidation state of the iodine here? +1. And the oxidation state of the iodine here +5. So iodine +1 to +5, it is converted. Now in this case, what is the oxidation state of the iodine? It is 0. Okay, I2 molecule, it is a neutral molecule. So +1 to 0. So reduction process is there. Okay, if we add, suppose that 2 iodide positive ion plus 2 electron, it will gives I2 molecule. So in this way the conversion will be takes place. Means oxidation state will be reduced here, reduction reaction. And this is oxidation reaction, IF to IF5, +1 to +5. Okay, so there is a gain in bond energy, so disproportionation will be takes place. So the tendency to disproportionate is common among the fluorides of iodine. Iodine. Generally, IF is converted to IF3, IF is converted to IF5, and also IF is converted to IF7. But if there is a gain in bond energy, then that conversion will be takes place, that disproportionation will be takes place. So disproportionation means the conversion of the lower interhalogen compounds to the higher interhalogen compounds. Okay. So you can see here the bond energy of the interhalogens of iodine, bromine and chlorine in their lower oxidation state is more than that of the interhalogens at their higher oxidation state. So in case of the CR, the bond energy will be higher here. In this case, it is 267.8. Bond energy will be less here because of due to the crowding here. The bond energy will be less here. This is because in iodine monofluoride, IF disproportionate to such an extent that its isolation has become almost impossible. Okay. Now let us going to convert the another disproportionation reaction. You can see here. IF it is disproportionate to IF3. IF it is disproportionate to IF3. So if we take 3 IF molecules converted to I2 plus IF3. So the single bond energy 277 multiplied by 3 IF molecules are there. I2, the bond energy it is 149. IF3, 3 multiplied by 272 here because 3 fluorine atoms are bonded to the iodine atom. So here the bond energy is less as compared to this because there are 3 bonds and there is only 1 bond. So bond energy will be higher here. So if we do this calculation, the energy of the product will be higher as compared to the reactant. So if we take this difference, it is 131.6 kilojoule. It means that IF is converted to IF3. Okay, there is a conversion of IF to IF3. Disproportionation of the IF to IF3 will be takes place because there is a gain in the bond energy. Okay, so conversion of IF to IF5, it has been already explained by us. Then conversion of IF to IF7. So you can see this reaction, disproportionation reaction, where it is possible or not possible. You can see here 7 iodine fluoride molecules converted to IF7. So +1 to +7 here, oxidation state. It is called as oxidation. And here +1 to 0, it is reduction. Here oxidation state is 0, +1 to 0 here, reduction. This is reduction process and this is oxidation process. So you can see here, calculate iodine fluoride 277.8 multiplied by 7, and here bond energy, if we do this, 2064. So in this case also there is a gain in the bond energy. It means that IF is converted to IF7. Okay. In case of first, 272 kilojoule is the bond energy of the single IF bond. Okay, single IF bond in IF3. Since there are 3 such bonds in IF3, the total bond energy in IF3 it is. So already we explained this, how to calculate the gain in bond energy, that is given here. Okay, so it is clear from the above calculations that the gain in bond energy when IF disproportionates to IF5 is the highest here, 248 is the highest as compared to others, whereas when it does disproportionate to IF7 it is less, disproportionate to IF5 it is also less. So that is the observation here. Now let us see the disproportionation of the IF3. Disproportionation of the IF3. How it undergo disproportionation, you can see here, IF3 to IF5. So see this reaction, 5 IF3 molecules we have taken, higher interhalogen to another higher interhalogen compounds. In previous cases, we have seen IF to IF3 disproportionation, IF to IF5 disproportionation, and IF to IF7 disproportionation. But now here the disproportionate is from higher to another higher interhalogen compounds, IF3 to IF5. So take the 5 molecules of IF3 and it is converted to 3 IF5 molecules plus I2. This is the product here. So consider here IF3 means 3 IF bonds are there. So 3 multiplied by 272. The bond energy it is 272 here and 5 molecules are there. So 5. So this calculation it is 4080. Now 3 IF5 molecules, 5 IF bonds are here. So 5 multiplied by 267.8. So in case of the IF5, the bond energy it is 267.8 for the IF bond, and 5 bonds are there and 3 molecules are there plus 149 of the bond energy of the I2. So bond energy of the product it is larger than the bond energy of the reactant. So gain in bond energy is there. So it means that IF3 is also converted to IF5. Disproportionation of the IF3 to IF5 is possible. Now let us see the disproportionation of IF3 to IF7, whether it is possible or not. Disproportionation of IF3 to IF7. So see here in IF3 there are 3 IF bonds. The bond energy of one it is 272. 3 bonds are there. 3 multiplied by this and there are 7 molecules. So 7 multiplied. In this case there are 7 IF bonds in IF7. So again the bond energy will be less here 231 because number of bonds are increasing. So it is very stable, unstable IF7 and 7 bonds are there. So 7 multiplied by 273, 231 and it is multiplied by 3. 3 molecules are there and twice I2. 2 multiplied by 149. Okay. So the bond energy of the reactant it is greater than the product. So there is a loss in bond energy. So this conversion is not possible because there is a loss in bond energy. As there is a loss in bond energy, that is not converted. So it is clear that when IF3 disproportionate to IF5, there is a gain in bond energy. Okay, you can see here IF3 converted to IF5, there is a gain in bond energy. Okay, whereas there is a loss in bond energy when it is disproportionate to IF7. When it is converted to IF7, there is a loss in the bond energy. Thus, the observed properties of iodine fluoride and IF3 disproportionating to IF5 and not to IF7 is justified by the determination of gain or loss in bond energy. Okay, so this is due to the greater weakness of the bond because in IF7 there are 7 fluorine atoms are bonded to the iodine. Crowding is very large here. So this bond it is bond energy is less because it destabilizes the molecule. As the crowding will be increasing, it destabilizes the molecule. So bond energy will be less here as compared to the other lower interhalogen compounds. IF it is 277, IF3 it is 272, IF5 it is 267.8, but in IF7 it is 231. Okay, so this is very less. So the lower bond energy in IF7 is due to two reasons. Why it is having the lower bond energy? Effect of steric hindrance is there because 7 fluorine atoms are very close to each other. Effect of steric hindrance as 7 fluorine atoms are to be accommodated around the central iodine atom. So lot of crowding is there. And second thing is that the resistance to the extremely high oxidation state. Iodine undergoes +7 oxidation state. So that is actually impossible. But iodine shows here that type of the oxidation state. Okay, so higher oxidation state, and also in the higher oxidation state s electrons are involved. Okay, so therefore it is somewhat difficult. So this is the reason why generally the disproportionation does not take place. So it is about the disproportionation of interhalogen compounds. Disproportionation of interhalogen compounds. So in this way, in this lecture, we has been discussed the general properties of the interhalogen compounds. Once again, I would like to revise these general properties one by one. So first general property we have discussed here, that is the bond strength of the interhalogen compounds. The bond strength of interhalogens increases as the electronegativity difference between the halogen increases. So to understand this, you can have to take the example of this. We can take the example of this interhalogen compounds. Let us see here. IF, first interhalogen compounds, then I uh, ICl, IBr. Okay. So in these interhalogen compounds, the order will be like this. Or we can take another example, iodine monofluoride, then bromine monofluoride, then chlorine monofluoride. So where is the electronegativity difference is larger? Here. So in case of the IF, the electronegativity difference is larger between iodine and fluorine. So it is having the higher bond strength. And as we know, bond energy, it is around 277.8 kilojoule per mole in case of the IF. This is because of the electronegativity difference. So higher the electronegativity difference, greater is the bond strength. Then heat of formation. Heat of formation among the interhalogen compounds decreases with the decrease in the electronegativity difference. That is the same reason. So in case of the IF, heat of formation will be larger. The same point we have to consider here, electronegativity difference between the two halogen elements in the interhalogen compounds. Okay. Then in interhalogen compounds, the less electronegative halogen shows positive oxidation state. So iodine shows +1, +3, +5, +7 oxidation state because its atomic size will be larger. Okay. And it is less electronegative element. So only iodine shows such type of the higher positive oxidation state. Interhalogens are more reactive than halogen except fluorine. That is true. Thermal stability of the interhalogen, IF, is highly stable as compared to other interhalogen compounds. Okay. So in this lecture, we discuss about the general properties of the interhalogen compounds. So all these properties are important. And last one, it is disproportionation. The interhalogen compounds can be disproportionated. Okay. The interhalogen compounds can be disproportionated. So this is about the general properties of the interhalogen compounds.